Hey y'all, I hope everybody is doing good. I hope you can see my screen. I've got a screen share going, so hopefully that all looks good. I'm just going to move this up a little bit. All right, so first up today, we are going to talk about radiographic exposure variables. So kind of the breakdown of what's going to affect how our radiographs actually look and how they're exposed. So, let's see. Okay, there we go. Okay, so the first thing we're going to talk about is the quality of our radiographs. So when we're talking about quality, that's not necessarily referring to positioning, that's referring to the actual image itself. So how easily can you see the different details on an image? And so like looking at this image on our screen, like that's really good quality radiograph. The positioning, not so great, right? The legs are a little wonky and stuff, but the actual radiographic quality, right? We have good contrast. It's not overexposed. It's not underexposed. I can make out individual organs and gas in the organs and such. So that's what we're referring to, how well we can see those details when we're talking about quality. Okay. And we know that there's several things that kind of combine to make either a good quality radiograph or a bad quality. So those are the things we're going to talk about. Okay. So there's five main factors that affect the quality of an image. So those are detail, density, contrast, distortion, and scatter radiation. So we'll go through each of those individually. So the first one we're going to talk about is detail. So detail is defined as the sharpness of tissue to organ interface. So the heck does that mean, right? So again, how well can you make out different tissues from one another? So how detailed, right? I mean, kind of what we think about with details with anything, right? How finite is something that you can see, okay? So when we can see all of those little differences, then we know we have good detail in our image. And there's two main things that affect our detail, and that's patient movement, right? So if the patient is panting or trembling or anything like that, you're going to get blurring, right? And so then you lose kind of that sharpness, that detail, just like when you're taking a picture and you've got a slower exposure time, right? Somebody's running, right? They're blurred. That's the same thing that we're talking about there. So to avoid that, we want to either take shorter exposure times, right? So less time, so there's less opportunity to see that movement, or we actually use sedation and or restraint devices for our patient. So, right, they're not, if they're sedated, they shouldn't be panting, hopefully. They shouldn't be shaking and all that. They should be nice and relaxed. So you should be able to get a nice, still patient so that you don't have any movement, okay? The other thing is what's called penumbra. So this is something that's a little bit outdated, if you will, because a lot of our newer collimators kind of negate this, but it's really just looking at kind of the blurring at the outside of an image. So like the inside where the center is nice and sharp, but as you move out further, it kind of gets blurred. So it kind of reminds me of when you do like a silhouette filter on a picture, right? So like if you put it around like your face where like your face is nice and detailed and then the kind of background around you blurs. So that's kind of what I think about when I think about that penumbra effect. Okay, so these are just some examples of blurring from motion. So finding good examples of this on the interwebs, not always the easiest thing. But you can see even that original image, part of it is because it was pixelated, right? And I had to blow it up, but kind of still not super great as far as detail goes, but those two kitty corner ones, the motion blurred and the blurred, right? You can see those definitely, you can't make any detail, right? It's just kind of all fuzzy. And then they have the sharpen image, which has kind of the best detail. So we don't usually use sharpen on our digital radiographs, but it is something you can do. You can do that with pictures you take on your phone and all of that too, to try and decrease that blurring, okay? All right, so other things that can affect detail. So we talked a little bit about focal film distance last week. So remember, the closer the distance, the better the detail, okay? So this is a little bit different than object film distance though. So object film distance, we talk about like if we lift them, right, we get magnification. Focal film distance is right from where you have your actual x-rays to your recording device, whether that's a cassette or the image plate for your digital and whatnot. So the closer you get actually with your focal film distance, the better the detail we get. But remember, land of opposites, and gotta play that kind of game of give and take here. The closer we get, we also get more radiation, right? Because it's more concentrated. The radiation isn't as spread out if it's closer. So kind of looking at that picture below, you can see those dots are closer together when you have that shorter focal film distance, which then ends up meaning that we have better detail, okay? But we know, again, if it's closer to the patient, we're going to get more radiation. So, again, we have to play this game. What's the best distance to minimize radiation while also getting the best detail? And so we have set out 40 inches is kind of our standard in veterinary medicine. And so that gives us kind of that even playing field of, okay, this is the best distance with the most minimal radiation exposure we can get, okay? All right, so that was detail. Next up is density, and we talked a little bit about density as well, but we're gonna go in a little more detail and kind of go back through because I know this is something that people struggle with. So density is, remember, the overall degree of blackness and whiteness on a film, right? How overall dark or light is it? So remember we talked about density, the main controller of density is MAS. More so the MA portion of that, but remember we pretty much use MAS as kind of our overall. We don't usually change things individually. So we're really looking at MAS here, okay? Because remember, MAS has to do with the total quantity of x-rays being produced. So more of those, darker film. Okay, so if the density of the film is too dark, it is overexposed, right? So this one on the right-hand side of your of the 3 images on the bottom of this slide. If the density is too light or underexposed, that's the left side, right? The center is kind of more of that ideal. And then if it's too light, it's underexposed, right? It's light overall. So it's not, we're not talking contrast, we're talking about overall, okay? And so too light of density, underexposed, too dark a density, overexposed. Other things, so if we are actually using film, we know that the temperature of our chemicals that we use to expose them and also how much time we spend in those chemicals will affect also the overall density of our x-rays. So if the temperature is too warm or the film stays in the developer too long, those are going to end up overexposing our film. Okay, it's giving more opportunity for the film to expose more. So we'll talk about film more in a couple of weeks, but just know if it's too warm or in the developer too long, it'll be too dark. If you use the opposite, if the temperatures are too cool or they're not in there long enough, it'll be too light. Okay, obviously with digital, that's not an issue for us, fortunately. Okay, so looking at our kind of schematic here, we have density in 2 different ways. So the first way on this last slide, right, we talk about the density of the film itself, of the image itself, right? If something is too dense, when we are talking about the film, it is too dark. If it is not dense enough or underexposed, right, it is too light. That is the film when we talk about density there. Now we also have to think about the density of what we're radiographing. So this is the patient themselves and or the individual things within the patient, like soft tissue, fluid, bone, metal, all of those things, okay? So the density of what we're radiographing means how thick or how high is the atomic number of those tissues, or maybe it's metal or something like that. Okay, so the thicker or the higher the atomic number of whatever we are radiographing, the less the x-rays are able to get through them, right? It's got a bigger barrier, so the x-rays aren't as strong to get through. And when those things are more dense, less x-rays get through. That means that whatever shows up on the image is actually lighter. Okay, so if you look at the bottom, that R for that marker is made of metal. That is the most dense thing that we can radiograph is metal. And so metal is usually white on x-ray because x-rays cannot get through and produce an image, okay? And then air is the least dense thing, right? It's a gas, we can't see it. There's no physical thing here, right? For x-rays to get through. So the x-rays go right on through, right? There's nothing, or for the x-rays to get stuck in. So the x-rays go right through. So that means that that film or that recording device is getting as many x-rays as possible. So it'll end up being darker in those spots, okay? So air is going to be the least dense thing that we radiograph. Like I said, metal is going to be the most. So from air, then fat's going to be your next least dense. And then we go to soft tissues, and there's going to be variations in there depending on the organs and the tissues themselves. Then bone is the most natural dense thing that we have in the body. And then, like I said, metal. So that's our markers. But also if a patient has any orthopedic implants, maybe even a pacemaker and they have metal wires in them, or maybe they got shot or injured or something like that, right? So, or they ate something metal that they shouldn't have. Okay, so all those things will show up white then on the x-ray. Okay, so remember, overall density is overall darkness and lightness. Something that is an image that is more dense is darker, an image that is less dense is lighter, an object that is more dense, so what we are radiographing is more dense, is white. Something that we are radiographing that is less dense is dark. Okay, so again, a little bit of opposite land, but if you break it down and you think about it, it's easier to go through it, okay? Okay, so how does the MA affect density? We kind of touched on this already, but when we define density, as far as the image goes, it is the sufficient accumulation of black metallic silver on the radiographic image. So that's when we're actually talking about film itself, right? Metallic silver has to do with the chemical reaction and stuff like that. Like I said, we'll go in more detail on that when we talk about film. But if we get more of that, then our image is going to end up being darker, okay? So how do we get more of that black metallic silver? We have more x-rays generated, okay? So again, up in our tube head, we're producing more x-rays, right? We know MA is that quantity portion of our x-ray, okay? So more of those electrons are being shot across. And then those x-rays have to make it through our patient too, right? So they have to make it through our patient and onto our intensifying screens or our recorder for our digital images, okay? But like I said, there's other things that can potentially affect density as well. We'll talk about the other main thing or the other thing in a moment, and we've talked about it already. But the main thing, the primary thing I want you to remember that controls density of a film is the MAS, okay? So if we have too much MA or MAS, we'll have an overly dark image. If we don't have enough, we're gonna have a lighter film, okay? And then again, when we talk about milliamperage, another name for milliamperage is tube current. So if you see that show up again, you'll know why. Okay, so MAS, and what we were talking about kind of the rules as far as density goes. So if we double the MAS setting on our machine, we are going to double the radiographic density. Means we are going to make it twice as dark. Okay, so an example of doing this using our equation for MAS. So if our original MAS setting is broken down into 100 MA and 0.05 seconds, then we'll have a total of 5 MAS. From there, we can either double our MA or we can double our time. So if we want to double our MAS, we can now set our MA at 200, or we can double our seconds to 0.1 second. And both of those will give us a quantity of 10 MAS. Okay, you will need to know how to do this because you will see it again on quizzes and such, okay? So the opposite is also true when we talk about making something lighter. So if we take our MAS and we cut it in half, then our radiographic density is going to cut in half, or it'll be half as light, okay? Or half as dark, depending on which way you want to think about it, right? So it's going to go from this darkness, it's going to be half that. So it'll be lighter, okay? So again, we can take this original equation. If we have a setting of 200 MA and 0.1 seconds, that gives us a setting of 20 MAS. And we can either cut our MA in half to 100, or we can cut our seconds in half to 0.05. Each of those will then ultimately give us 10 MAS. Okay. So I know I just said halving and doubling and all of that's going to half and double, but when you're looking at an image and you go, oh, that's too light or too dark, how do you know how much to actually change it by? So it's not I don't want to say it's a rule, because the next part is actually the rule that we use, but the consensus is that we have to change our setting by at least 30%, either up or down, to barely see a difference with the density of our image. So we don't want to change it where it's just barely, right? If it's close enough to just barely change it, then it's not worth taking our time and the radiation exposure and all of that to change it. So if it's too light or it's too dark, we are going to double or half our MAS by 50%. Okay. So, because 30%, we're going to kind of have to put on, our magnifying glasses a little bit, or imaginoscope, and be like, oh yeah, that was a difference. If we change it by 30%, but 50%, we can definitely see a difference. Okay. So like I said, if we don't need to change it, either double it or half the lightness or the darkness by 50%, then we're not going to take another exposure, because instead we're just wasting our time. And like I said, exposing our patient and ourselves to more radiation that's not necessary. So if it doesn't need 50% change up or down, then we're not going to change it. Okay. If it is too light or too dark and we want to make it lighter or darker, we are going to do it by 50%. Okay. So here's some, not examples of that 50%, but just kind of looking at, we're only going to look at the top since we're talking about MAS right now. So that center image is kind of an ideal perfect image, if we will. If we look to the left, it is underexposed, right? It's too light, right? We're not getting great detail or anything like that. It's just kind of too light, okay? On the right, you can see we've burned through that bone now. It's too dark, right? The bone shouldn't look black on X-ray, right? It's supposed to be white. So that center image is that ideal. The right side is overexposed. The left side is underexposed. I hope your left and right is the same on your screens as it is for me. It still says under and overexposed, so hopefully. Okay. Like I said, we're going to talk about KVP here in a little bit. So we're just looking at MAS for this image. Okay. All right. So that is density. Next up is contrast. So we talked briefly about contrast being the controller of, or KVP or kilovoltage being the controller of contrast. So when we talk about kilovoltage, that is defined as a measure of that maximum electrical potential across an X-ray tube expressed in kilovolts. What the heck does that mean? That's how strong those electrons are getting pulled across and then pulled down as X-rays through your patient. Okay, so that strength of them. So a higher electrical potential, they're stronger, they're able to penetrate through your patient more easily. Okay, so if we have a thicker or more dense part of the body, we need more KVP, because we need to be able to penetrate through that. If we don't get enough X-rays through, then our image is going to be too light, right? Because there's not enough exposure onto that cassette. So thicker, more dense things, we need a higher KVP to make our way through. Okay, so if we increase our KVP, we increase that acceleration of those electrons, we make them shoot across faster. If they shoot across faster, then they're able to penetrate through whatever object we were radiographing, most likely our patient, right? They're able to better penetrate through our patient. So that's a good thing, right? We want to be able to penetrate through our patient, right? We can get better detail on that, better contrast, and kind of instead of being just kind of overall gray, okay, or overall white or whatever, depending on the density that we set. Okay. Problem with increasing our KVP is that is going to increase our scatter radiation, right? It's going to bounce off more. Okay. So again, a little bit of that give and take. The other thing we need to remember is using a higher KVP, better penetration will also allow us to use less MAS. We don't have to use as many total x-rays when it's able to go through the patient more easily. Okay, because we don't need just a lot of kind of weaker x-rays to kind of get to the same level if we use fewer stronger x-rays to get to the same place. Okay. It also allows us to kind of decrease the work and the force put on that tube, which decreases the heat, which means that our x-ray machine will actually last longer, which is always a nice thing too, because that's an expensive piece of equipment. Okay. So like I said, there are other things that affect density, and KVP is one of those things. Okay. But the main controller of density is MAS. Okay. So when we're talking about KVP and density, though, we know that density will increase with an increase in KVP, which makes sense, right? If we have stronger x-rays, more get through our patient, that means more are going to hit that recording surface or that cassette, and the image is going to get darker. Okay. So that energy increases, increased penetration, but we also will get more increase or more scatter from that. Okay. So that is something we have to keep in mind too. Remember, there's always some give and take here. So like I said, even though changing our KVP can affect our density, that's not the main thing we want to change if we are trying to change density, right? If the image is too light, I'm not going to go, oh, I'm going to increase my KVP to make it darker. I'm going to increase my MAS to do that. Okay. If I've hit my max one way or another, maybe I will use my KVP to adjust that. But for all intents and purposes, MAS we are going to use to change the overall lightness and darkness of our image. Okay. Because remember, affect our KVP, changing that too much up or down will also affect our contrast, which then may not give us a high quality image either. Okay. So KVP also has its kind of own set of rules for how and when to change things, just like MAS, but numbers aren't quite the same because that would be too easy, right? So our rules for KVP is we are going to increase by 15 or decrease by 15%. Okay, so increasing by 15% will increase penetration of the region of interest, which is what we want to see on the patient, right? So region of interest could be the heart, it could be the elbow, whatnot. Okay, so that's region of interest. So if we do increase our KVP, we also have to remember that it's going to affect our contrast. So increasing KVP will give us less contrast, which means we have more grays, right? We see all those soft tissues structures more easily. Okay, remember opposite land, increase, decrease, increase. Okay. If we decrease by 15%, we're decreasing the penetration of x-rays through the patient to that region of interest. Okay. Again, we're going to affect our contrast by doing that. So if we decrease our KVP, we're going to have more contrast, which means we have less grays. So it means we have more black and white, right? We're more at the ends of the spectrum versus all that grays in between. Okay. So we have to remember, keep that in mind. You know, are we more concerned about the contrast? And is that why? Is it too many grays or too few grays? Okay. So that's when we want to adjust our KVP. Okay. So things that we need to take into consideration and things that are going to affect our contrast. We already talked about density. Okay. So the density of your patient or whatever we're radiographing affects our abilities to absorb X-rays, right? So if something's really dense, it's going to absorb more X-rays than something that's not as dense. So we know based on the atomic number, like we said, and the thickness of that will affect our ability for our X-rays to penetrate through. So this picture, we're looking at these arrows. So the arrows, you can see the big fat arrows on the left-hand side are all the same number of X-rays. Okay, those are coming from our X-ray tube. Okay, they're all equal. The pink, the kind of salmony color, and then more of that red color, that is what we're considering the density or the thickness of the tissues. Okay, so the pink is less dense than the red, right? So the pink is the least dense, the red is the most dense because it has the most color. So you can see the arrow, the X-rays that get through the pink are pretty good, right? It's almost the same size as the X-rays that left the X-ray or that left the tube head. Okay, so that's going to give us a darker image on our film, okay, on our radiograph. If you skip to the bottom with the red box, you can see that arrow got a lot smaller because that red is more dense, so less X-rays can get through it, which means then it ends up white on our image. Okay, so hopefully that's gonna kind of helps you guys. And remember, air is going to be the least dense thing, and then we go fat, water, muscle, then we go to bone, and then metal is going to be the most dense thing. Okay, so think of the metal as the bottom and your air at the top, and then you kind of have those soft tissues and fluids and stuff in between that, and your bone as well. Okay. Okay, so how is KVP affecting our contrast? So like I said, contrast will decrease when you increase KVP because we are increasing X-ray energy, we are increasing penetration, and we are also increasing scatter radiation, which kind of overall makes the image darker. And we'll talk about scatter radiation here more in a little bit. So a low KVP means we have high contrast, right? More black and white because we have less X-rays penetrating through the patient, more absorption of those X-rays into the patient. So we have that shorter grayscale, means more black and white, right? It's a starker difference, just like that image in the picture of that bone, okay? So that's what we want to use a low KVP for, is bone, because we don't need to see, right? Bone's all pretty similar density, so we don't need a bunch of little random grays and stuff like that in there. We don't need that for bone. On the opposite end, a high KVP, we have lower contrast because we have more penetration, right? More X-rays are making it through the patient and less absorption into the patient of those X-rays. So we have that longer grayscale, right? Low contrast means longer grayscale, means there's more grays, okay? So there's less stark difference between all the different shades there. Okay, so you have that long grayscale, and this is what we want to use for soft tissue because the stomach and the spleen and the liver and all of that are really close together in density. So if we don't have just those minute differences, we won't see any of those individual organs. Okay. All right, so again, this is talking about contrast and kind of that grayscale. So when we say we have high contrast, which means we have more of that black and white and less gray, it means we have a narrow latitude, right? It means there's fewer colors, if you will, on our image, okay? More of that black and white, less of the gray, okay? And we know that when we have that lower KVP, that means if we change it by just a little bit, we will actually see a noticeable difference in our image. So if you take a low KVP, say your KVP was like 40 or something like that, and you change it to 45 and you leave your MAS the same, you'll see more of a difference compared to when we have a higher KVP. We actually won't see as much difference if we make a small change in that number. Okay, so say our KVP is 115. If we make it 120, we're probably not going to see a difference in our contrast. Okay, we're not going to see a difference in those grades. So remember, low contrast, high KVP It means we have lots of grays and a wide latitude, right? There's lots of those shades. Okay, so it's a longer spectrum of grays in there. Okay. When we talk about wavelengths for our KVP or for our radiation, if we increase our KVP, our wavelengths actually, do I have it on here? No, I don't. Okay. Our wavelengths actually get shorter. Okay. And we know the shorter wavelengths penetrate through things much more easily than longer wavelengths. So we have to keep that in mind. Okay. So that's the same thing looking at another reason why KVP changing that helps us. The higher KVP gets better penetrations because those wavelengths get shorter and we know those penetrate more easily. Okay. They're faster, they're stronger, right? So they're getting through our patient more easily. Okay. Next up is distortion. So this one's kind of I want to say it's weird, but it's one of those things we can have it and not even realize it. Excuse me, but parts of this we can actually also use to our advantage. So let me get a quick drink and we'll talk about that. Okay, so distortion kind of by definition means we're misrepresenting the size, the distance, or the shape of an object. So the big one we think about and we like to talk about is magnification. So that's when we magnify, right? We make the overall size of our image bigger or smaller, mostly bigger, right? When we're talking about magnifying, okay? And we talked about OFD last week, right? Our object film distance. So if we increase our object film distance, so if my hand here is the table or the recording surface, to minimize magnification, I want my object that I'm radiographing as close to that as possible. But if I raise up that object, then I start magnifying. So again, if you take your phone and you turn on your flashlight and you take your hand and you move it up and down, you can see that your shadow gets bigger and smaller based on how close your hand is to the table or the desk or whatever you have your hand over. So the closer it is, right, the more true to size it is, the higher up it is, the bigger it gets. Okay, so that's that magnification. Now, foreshortening and elongation, if you've had dentistry already, we've used these terms. So this is when we're talking about distortion, making something smaller. So foreshortening, right, making it smaller, or elongation, making it longer. Okay, and I've got some pictures to go with that here in a second. So this has to do with still distortion, but it's because it's changed, not because of full up or down, right? Like we have with magnification, because that's level distortion. It's equal overall. So foreshortening and elongation is when we start kind of rocking the boat and changing our angles a little bit, okay? So that could be changing the angle of what we're radiographing, okay? It could be changing the angle of our actual cassette. So obviously if you're using a table and you have your cassette in the bucky tray, you're probably not going to do that. But if you are out in the field with an equine patient and you're holding the cassette, and you change the angle of that, right? It's not perfectly parallel with your patient, then you can for sure get distortion there. And then you can also get distortion if you change the angle of your tube head, which most of those tube heads, even though they're stationary in our tables, you can usually adjust the angle because there are some images in positioning where we actually do want to tilt that. Okay, so it's not necessarily, but you can also take, you know, like the mobile ones where I said the tube can swing and go, you know, 90 degrees. Okay, so if the angle of that is not parallel to your recording surface, okay, so if this is my recording surface, and then this is my tube head, these have to be parallel. This is probably not the best picture. These have to be parallel to each other. If I start changing the angle like this is when I'm going to get distortion, right? And then we talked about that, like I said, in dentistry, when we are coming in, because we can't always have things parallel in dentistry, okay? Because teeth kind of get in the way and the rest of the mouth and all of that, okay? Magnification, I think I talked about it last week, but magnification I can use to my advantage. right? If you think about your teeny tiny patients, like your mice and your rats and kind of a lot of your exotics, they're small, right? And so seeing an image that's, this big on the screen, I might not see everything. Now, if I take that patient and I put them up on a box that's radiolucent, right, where the x-rays can still go through, now I've just made them bigger so I can actually see things better. Okay, so I can use magnification to my advantage in some cases as well. Okay, so here's just some schematics of those different things. So the one on the left, right, where the bone is parallel. Okay, so that's just magnification. You can see that the shadow or the image on your plate there has gotten bigger. And then you can see we've got that foreshortening and elongation, okay, and some of that magnification going on when we change the angle of the bone or we change the angle of the plate, okay? Okay, the heel effect, also known as the anode heel effect. So this can definitely be confusing. So I want to kind of walk through it. So this is defined as an unequal distribution of X-ray intensity and it being more intense on the cathode side. It's kind of frustrating that it's not the cathode heel effect, it's actually called the anode heel effect. So even though we talk about it being more intense on the cathode side, we call it the anode. I don't know, I didn't name it, right? But what happens here, so you can see in this picture, and we talked about it last week. So that blue thing in the picture, that is our rotating anode, right? We have that disc and, think of it as a plate when you look at it from the other angle, right? We're looking at it from the side on this picture. In the front, it's a plate and it's always hitting kind of at that same spot as the plate spins. From the side, you can see we have that angle, okay? And so if you look at it, right, here's kind of that angle. And then if these are my electrons coming across, if they hit the up here versus down here, these electrons are stronger that hit up here versus the electrons that hit down here. What that then equates to, strong electrons hitting here is stronger X-rays coming down, okay? Weaker electrons hitting down here, weaker X-rays coming down. So we have more X-rays, stronger X-rays on the cathode side than on the anode side. Okay, obviously they're also coming off of the anode, but what we're saying is by cathode side, it's the side closer to the cathode, right? Because that angle is, they're not penetrating, or the X-rays or the electrons are not traveling as far from the cathode to the anode. So that's the cathode side, right? That shorter distance is the cathode side, is what we mean by that. Okay, so we can actually use that to our advantage. So we can know that, hey, X-rays are stronger on the cathode side. We're going to put the thicker part of our patient on that side. Okay, so that it ends up kind of equaling out, right? Not every patient, everything we radiograph is perfectly thick, the same thickness all the way across, right? Think about dogs with big broad shoulders and kind of teeny tiny little thorax, right? Got all this muscle up here and then they kind of do one of these. Okay, so it's thicker at the front of the chest and thinner at the back. Okay, so the front of the chest on the cathode side, back of the chest on the anode side. Okay, and remember, you can see that on your table. Again, usually the case is that if you put your head to the left, right, that helps us with this anode heel effect. So, but again, break it down, cathode side creates stronger X-rays. Okay, so they're going to penetrate through our patient better. And so we want the thicker portions then on that cathode side. So then what everything goes through, it kind of goes through equally. Okay, if you still are struggling with that concept, let me know, but hopefully that helped. Okay, next up is scatter. So scatter radiation. So we talk about, right, this is the stuff that's bouncing off and not going into the patient or through the patient to your cassette. Okay, this is the stuff that we use our PPE for because we can't see it and we have no idea where it's going, okay, or where it's coming from, because it can bounce off the table, it can bounce off the leg or the head or whatever we're radiographing, okay? So, and then we don't know even though it's bouncing off, we don't know which direction it's gonna go in, right? It could go to the left, it could go to the right, it could go straight back up, okay? So, even though these X-rays aren't as strong as coming from the primary beam, we should know we're keeping out of the primary beam, right? We know that our collimator gives us a light where that primary beam is gonna be. So we know we need to stay out of there, but like I said, we never know where the scatter radiation is gonna go. So that's why it's more dangerous to us, okay? The other thing too, it can bounce off of stuff and then still go through and hit our recording surface, right, our cassette. And then that affects the quality of our image as well. So it can kind of give an overall graying to our image, which we don't want that because that affects the quality of our image, okay? So something we have done is adding a grid into our table to help us absorb some of that scatter radiation. So we'll talk about the grid and what that is here in a minute. And then, like I said, I also brought up collimation. So that's taking and trying to reduce that primary beam, because then we have less X-rays kind of coming out, right? Which means there's less scatter radiation there as well. Okay, so when you're trying to radiograph a finger, collimate it down to the size of the finger, not, the size of my entire screen. Okay, because more radiation with a bigger collimation area means we're going to have more scatter there as well. Okay. Okay, so our grids. So this is what lives kind of under or within our tabletop. Okay, so it's going to be between our patient and our Bucky tray. And these are little metal slats basically that are going in there. So they're made of lead. So we know lead is going to absorb those X-rays. And it really helps us focus those good X-rays, those straight down primary X-ray beams that are going to give us the best image possible. Okay. So like this picture, right? That primary beam is coming straight down, right? Nice and perpendicular to it. That scatter can come down and go in different angles. And we don't want that scatter. That's kind of that extra light, right? Kind of coming in and affecting the quality of our picture. Think of it as, when you are taking a picture and you kind of have that sunbeam coming in, right? It's not actually part of the picture, like somebody's face or something like that, but it is affecting what that image looks like. Obviously, a lot of people like to add it for kind of that cool effect. But if you're just trying to get what's in front of you, like somebody's face or something like that, you don't want that there, right? It affects the overall quality of the image of somebody's face or something like that. Okay. So kind of think of it as trying to block that out is what the grid's trying to do. Okay. Also, the grid is going to help us increase contrast. Okay. Because again, we're only going to get these quality X-rays that are kind of true to what went through the patient. The scatter is going to add to the overall density, which then negatively impacts our contrast. So grids increase contrast because it's taking out that scatter radiation. Okay, so we have different grid systems, if you will. So there's grid ratios. So that's what we're looking at is the height of the lead compared to the width of the space between them. Okay, so if you have a 2.5 millimeter high piece of lead and it's a 0.5 millimeter apart, it's going to be a 5:1 grid ratio. Right, the higher the ratio, the better it is at absorbing scatter radiation. Right, it's going to get just the best of the best of the best of those X-rays going through. Okay, so least effective on our ratio is 5:1, 15:1 is our most effective. I always forget to look. This 8:1 was our old table. I don't know if that's the same for our new table. I always forget to check before each time I teach this, and then I get here, I'm like, ah. Anyway, but like I said, higher the grid ratio, the more efficient or effective, like better quality our image is going to be. But guess what? There's always give and take. If we have a higher grid ratio, guess what that means? We have to use more X-rays to get through because it's going to absorb a lot of scatter, even that little minute change. Okay, so we have to take that into consideration as well. Okay, because it can absorb that primary beam too, right? Depending on exactly that angle. So we have to increase our MAS to make up for that, okay? Because we need more x-rays to make it through to get to the same image, okay? And like I said, that grid, it's in that tabletop and it's usually centered. It's usually not the entire tabletop, which is why we want to try and get our patient centered on the table as much as possible. So don't try and take radiographs right, down in the left-hand corner. Try and get whatever you're radiographing in the center of that table as much as possible, okay? All right, let's see. So here's an example of taking a radiograph with a grid and without a grid. So that top one's with a grid. You can see that is, it's still not a great radiograph. I will give you that, right? It's a little underexposed, right? Because it's overall really light. But if you take that grid out, you see it's darker, but it's overall more gray. You actually make out less in your image, right? I can see the bones still, but I don't make out any organs in the abdomen, right? It just looks like it's a skeleton. It doesn't even look like there is soft tissues in there compared to the top one, where at least I can make out some kidney and intestine and bladder and stuff like that, okay? So that's the difference between with a grid and without a grid. All right, and then our collimators. So like I said, the collimator is that light source, okay? So it's adjusting these little LED kind of window, and whatever that light is that we see is what the actual X-ray beam comes out. So that little picture on the bottom right, we have a bigger X-ray beam that is created with every single kind of click of the pedal, but that doesn't mean that all of those X-rays come out every time, okay? It just depends on how much we have that collimator open or closed, okay? So we are gonna adjust that, right, to be just what we want to radiograph on our patient, okay, to minimize that scatter radiation, okay? It also, too, especially with digital, not so much with film, but if we collimate it down, it'll actually then give us a bigger version of that image on the screen. So kind of like magnification, if you will, right? You kind of crop it down. It's kind of like cropping, really. So if you take a screenshot of something, but you only want what's in the center and you crop it down, then that whatever's in the center gets bigger. Okay, it doesn't necessarily blur it like it would for cropping, but kind of think of it, it just trims it down to give us exactly what we want. Okay. All right. So this is just a picture showing us how much collimation will reduce the scatter in a situation with our patient, right? So you can see on the left, there's no collimation. There's lots and lots of scatter radiation because there's lots of X-rays floating around. We collimate it down, just looking at a specific area, that scatter radiation reduces significantly. So I always like showing these kinds of pictures. You don't get to see this really with digital, but those black arrows on this picture are actually pointing to where the collimator was kind of set, if you will, on this patient. But you can see there is still stuff being picked up all around this image. That's all from scatter radiation, okay? So this is why having your fingers just outside of the collimator doesn't mean that you shouldn't have lead on. As you can see, there are still X-rays penetrating through and getting onto that film, okay? Which means then that your fingers and all of that, if they're right there, they're also still getting exposure from that scatter, which is why we want to wear the lead gloves, okay? So just because you're outside of the collimation does not mean that you are in the free zone. All right, that is that. So again, you have 5 controllers of, I hope I'm not making you guys sick, of image quality. Remember, detail, density, contrast, distortion, and scatter radiation. Okay, so know those, know which each one does, and how it is going to affect your image quality. All right, I hope this helped, guys. Have a good one, and I'll talk to you soon.